Hey guys, let's do multiple linear regression part 2. So this time we're going to do hierarchical regression. And so what we're going to do is we're going to take everything we did in that last regression video, including the brand new fancy data screening procedures, and now do our regression analysis in steps. So the really nice thing about hierarchical regression is that sort of like step 1, step 2, step 3. Now, that being said, JASP doesn't quite have this function, so we're going to kind of fake it till we make it, because it allows you to do things in steps because you can just do the analysis a couple times. And there is this step function in there, but I'm going to tell you not to touch it because it's not what we're trying to do in this particular analysis. So that being said, kind of a reminder, why hierarchical regression again? Okay. Other than your instructor cannot spell the word hierarchical to save her life, which is, kind of obvious, I think, given the fact that I think it's misspelled right here at the top. So, is it? Let's ask this question today. Hierarchical. Shouldn't have a C? It should have a C. Hierarchical. Okay. So, why do this, especially if poor Dr. B can't spell it? And the purpose of it is as usually as a control. So I want to control for some variable, nuisance variables, noise variables, or just some things first, and then see what happens. So this allows me to, in this particular example, control for gender and age, and then tell how much this other thing adds to the equation. So this is where PR squared is going to be pretty important. But really, it also allows me to do sets. So we started this lecture 2 videos ago talking about dummy coding. And I said dummy coding is kind of a pain, but you can do that when you want to mix and match variables, variable types in regression. Well, if you have 3 continuous variables and 1 categorical variable, and you're really interested in it, you can't quite do that in an ANOVA analysis. You might be able to hack together an ANCOVA, but ANCOVA is not the best thing in the world. So instead, what you can use is a hierarchical regression to take all of those dummy-coded pieces and control for them in one step. So before we said, well, it's 1 predictor, but because, we have 4 groups, actually 3 predictors, this would allow you to sort of group them all back together in a specific way. So we're going to use a dummy-coded variable in this example, but it's a simple one. It's gender, so it has 2 levels. And remember, quiz question, how many dummy-coded columns do you need for to run these types of analyses? And it's levels minus 1. So the nice thing about having 2 levels is it's already pairwise, and so we only need 1 column because it's 2 minus 1. But we are going to kind of work with a dummy-coded variable in this example just to kind of remind you of what was happening before. So we're going to look at the gender of participant, and I've showed you how I've coded it. So I don't want to use words because it won't let me use words. It needs to be in numbers. The age of the participant, their extraversion. We're going to use that to predict how well they take care of their car. So I love book examples because they're cheesy. So we did books and grades in the last example. We're going to do car care maintenance in this example. But if you want to think about your own research, this might actually be very important. So I could look at the control for the gender and the age of a participant, and then look at how well I can predict, using this personality variable, how well I can predict getting along with others. So if you're interested in psych and maybe IO psych, how well do they work in teams? I could control for gender and age and then use a personality characteristic to look at how well do they adhere to the medicine plan that the doctor gave them. So personality might be a good predictor of like adherence to treatment plans. And then I'm trying to think athletic training, get you guys in here. I could control for these demographic variables and then look at their personality. Again, maybe how well they can get along in teams, because that's a relevant question. But but also it could look at like whether or not their personality predicts if they're going to return to sport faster, right? So if they have the right type of personality, they're going to listen to what you tell them to do, and they might return to play quicker. Just kind of give you guys some examples of how this might be relevant to something that you might be doing, because those are all words I can pronounce, unlike some of the research that people are doing with words I cannot pronounce. Anyways, so let's try looking at power for this one. Okay. And actually, we're going to think about R² increase here. So this is going to be just a touch different than what we did last time. So I'm going to pull up GPower here. Click on F test. This time I'm going to go down to linear multiple regression fixed model R² increase. Okay. And then what that does is it actually tells me how much of an addition is my last step. Generally, you're doing this analysis if you're interested in especially the last step. You might be interested in all of them, but that last one usually is key. Otherwise, why are you doing it? So I want to know how much this extraversion adds above and beyond everything else. So this is where R² increase gets in. So how much am I adding to the equation? Otherwise, it looks very similar. So I click determine. I can do direct, and it's partial R². So what did I do in this example? Let's do a medium effect size, so 0.09. Calculate, transfer to main. Now look at all this, looks pretty simple. 0.05, 0.80 for power. Number of tested predictors, how many are in the last step? Well, we're going to do gender and age first, and then add extraversion. So there's only one in the last step, but there's 3 overall. So number of tested predictors is the number of predictors in the step you're interested in. Total number of predictors is obvious, it's the total. So hit enter. Tells me I need 82 people, and I don't remember how many I have, but 82 is not bad. Okay. Right. Make sure that all matches. Ta-da. Okay. We'll come back to this results section here in a second, and let's just try this analysis. So let's get rid of GPower here. And I'm going to click over here and open the data set. This is data set 2. Let's see if we can screen this data set. Excuse me. Okay. Make it bigger here. I'm going to call this my master data. Okay. And let's check for, first of all, accuracy of the data. Highlight this, and you'll see that I have gender or sex or whatever you want to call it over here already coded as 0s and 1s. If you did not have that coded as 0s and 1s, you would want to, because it won't let you run analyses on words. So you need to dummy code it or fake code it as 0s and 1s. And remember, 0 is going to be the control group. That's true even if I have one column. So we're going to do female compared to male. All right. So I'm going to click data, data analysis. Right, we're doing accuracy. So we're going to go up to descriptive statistics. In this particular case, I'm going to highlight all of them. Labels in the first row. And click OK. Oops, my fault. Click summary statistics and then OK. Really interested here, right? So nobody's outside the range. It's all 0s and 1s. That's good. Our age here is 21 to 58, so no negatives. Great. Or no like toddlers that can't wash cars. Right? Our extraversion here, I don't remember what this runs to. Let's pretend it's 0 to 100. And our car maintenance score is also 0 to 100, just to make something up. So we don't really have any problems with our data. So I know we started the year by like really talking about like fix these scores. But in real data that you've collected maybe through Qualtrics or SurveyMonkey, happens a little less, and more becomes an issue of making sure your scales are coded the way you think they're supposed to be coded. So one problem we have when we collect scale data is, let's say it's supposed to be 0 to 6 randomly. Well, Qualtrics, I think, automatically does 1 to 7. And so those are more the problems you're troubleshooting, less problems where the data's actually out of range. It's more like, is it coded correctly? Just kind of an aside. So our accuracy is okay. Now let's try, see if we have any missing data. And I wish it would keep the same, I need it bigger because I'm blind version, but that's an aside as well. So we've got accuracy. Let's check missing here. Let's do missing by participant. So this is percent valid. Right. We're going to do equals, count A, open parentheses, highlight everything, divide by, I have 1, 2, 3, 4 things I'm interested in, times 100. Okay. Go from white arrow pluses to black pluses. Double click. Right. We can kind of scroll through our 40 plus participants. We look okay. Right. So remember, if you have enough people this way, you're not going to have any problems by column, but we're going to calculate it anyway. So do equals count A, open parentheses, highlight everything. Okay. I'm hitting Shift Command up or Shift Control up to do that kind of quickly. Close parentheses. We're going to divide by 40 participants. Yep. Times 100. Oops, I don't know what I just hit. Okay. White plus to black plus, drag across. So we don't have any missing data. Woohoo! Yeah. So no accuracy problems, no missing problems. Let's do outliers. So let's see what happens when we look at the z-score for all of these columns. So there's no point in doing an outlier analysis on a categorical variable. Just don't do that because it's categorical. Even though I've got it coded as numbers, remember it's still categories. So we're gonna do z age, z extra, and z car here. So it's equals, open parentheses, click on the first data point, minus average, open parentheses, highlight the whole column, close one more time, divided by STDEV, open parentheses, click on that whole column again, close parentheses. Remember, hang on to your parentheses. And then I'm going to take that, go from white plus to black plus here on the corner, drag across. Oh, come on. And then double click to get everything going down. So that gives me all the z-scores for everybody. Highlight these bad boys, make sure you're on the Home tab. Conditional formatting, highlight cell rules, greater than. It's 2.99. We do the same thing. Conditional, highlight cell rules, this time less than, negative 2.99. Hit OK. And I've got some people who are close. Right? So they're high extraversion and high car maintenance, but I don't have any, I don't think, it looks like, that are outliers. Okay, so we don't have any outliers based on each individual column, but we're also going to check JASP for the standardized residual outliers. See what happens there. To check for additivity, I'm really interested in just these three. I could correlate it with car, but remember that's the point. We want it to be correlated with the DV, so let's not do that. So I'm going to click Data, Data Analysis, go up to Correlation, OK. Highlight the three I'm interested in. I do have labels. Let's see if it'll run. Okay. So I don't have to exclude car. I just didn't run it this time. Now this is a correlation with a categorical variable, which is a little odd, but it essentially tells you whether or not there are any differences between the two groups on that variable. But we don't want them to be perfectly correlated with another variable because that implies that knowing gender in this example, would perfectly predict their extraversion, right? Then that would still not be good. But I don't really have any problems, right? All of these are less than 0.9. So I'd say we're pretty good to go. So I'm going to make my final data set here, just to use for my graph here in a little bit, and also just to have it in case I get confused later. And you could put these in any order on the bottom you want. I'm just doing them like order left to right that I went in. And I didn't change anything about the data set, so I'm going to actually use my original one to pull into JASP here. So let us open that file. So I'm going to click File, Computer, open this example, CSV files. If you have any problems with these files, open them in Excel and resave them as CSV. For some reason they're saving themselves as text files. That may cause you some trouble. So we're still data screening, so let's click Regression, Linear Regression. Car is our dependent variable. We're actually going to use all three. Okay, this is not the way we're going to run that final analysis. This is data screening only at the moment. Okay, this is important. Data screening only at the moment. Under assumptions checks here, I'm going to do my normality first. So residuals histogram and standardized residuals. That's looking pretty good. It's centered over 0. It's between 2 and 2. I wish it weren't bimodal. So we got a little modality action happening here. So I wish this one were taller, but it's okay. Maybe a little skewed. So the nice thing is it draws the line for you. Okay. So maybe a touch skewed. There's a little more stuff over here. Our QQ plot, which will give us linearity. Look how gorgeous. Oh, it's so beautiful, right? All those dots on the line. Last but not least, residuals versus predicted. Nice spread across 0 this way. Nice spread around the middle. Maybe slightly more dots over here. But I'm not too thrilled with this sort of diamond shape. So you see how it's kind of got this V shape down here. And I have to think about, is it just this one dot that's causing this? Not quite. So this is a little heteroscedastic in the sense that it is making this weird kind of upwards megaphone. Okay, so that's slightly problematic. The bad thing about heteroscedasticity is it lowers power. So I'm going to try this analysis anyway, but know that there are other options that you can do. I mean, the point of this is to teach you multiple hierarchical regression, but know that this is slightly problematic. Okay, the last thing we can check for assumptions before we get into the actual test is click Statistics, and I'm going to click Casewise Diagnostics, and I'm going to make sure it doesn't pop anything up. It seems like you're doing something wrong because nothing appears here. So you actually click all cases if you wanted to see every single person's standardized residual, and it actually gives you the predicted values. Ooh, fancy! Okay, you're going to watch me in a second video figure out something that I should have learned in the first videos. So we could actually use this to make our graph if we wanted to. Ooh, let's do that. That's easier. Sorry about the first one. Learning things as I go as well. Anyway, you can actually pop up and look at all of them. So it's not like you're doing anything wrong. Click on this, get this back up here. When you don't see any, it just means there aren't any that are above 3. Ooh, but let's hang on to this little bad boy right here. So I'm going to cut and paste this and write in my Word document, sort of data screening only. Paste that. All right, and then let's make these stupid pictures smaller so that you guys can look at them later. And then I'm going to do one more thing. Well, actually, I'm not going to do anything. I'm going to think about something and do it here in a minute. There we go. All right. So this is for data screening only. So we're not going to interpret any of this analysis because it is not quite the analysis we want. So instead, we want to go down to, let's see if I can spell this right this time. Hierarchical regression. So let's actually try that regression now. And if you find it confusing to have both of these in here at the same time, where you have data screening or we are turning them off, you've already cut and pasted in a word, just delete it, get rid of it. And that might help you not look at the wrong thing. Okay. So we've gone all the way through data screening and maybe a little problems with heteroscedasticity. Okay. Let's try that regression. But this time I'm going to take out extraversion. So it kind of reset everything over here, which is great, but I'm going to turn a lot of this off this time. Go away, go away, go away, go away. So we're going to turn off all the assumptions checks because now we're not concerned with them. And we're going to do step 1. Now when you do your steps, be sure you write down what is going into your steps. And they are additive. This is the thing that everyone messes up on their first try, is that steps are additive, not replaced. Okay. So I'm going to take my first step, which is going to be age and sex, and I'm going to put them into my analysis and only look at them. Okay. So we're going to add R-squared change here in part and partials when we're running the actual regression, and this is going to be step 1. So you'll see extraversion over here is hanging out, waiting on its own turn. So my copy. And here's step 1. Step exclamation point. So here in step 1, is the addition of these two variables significant? Right. So we're gonna report this like we've been doing. So we're interested in these down here. So I've got 2 and 37. Notice a lot of these numbers are the same because it's just manipulated book examples. This is 19, 25. P is less than 0.001. Sorry, little p here. Oh, I still have caps lock on. There we go. And our R squared is 0.51. Why did this change to some weird font? Whatever, it'll be in a big giant font, 0.51. Okay. And so yes, this is significant. It's 51% of the variance. Hot damn, that's a lot. Okay, so 51% of the variance in car maintenance is due to gender and age. Now let's go down and look at those two variables. I don't want to be in that box. See what we can find here. So let's talk about sex. Now I have a song stuck in my head. Let's not do it. Let's keep going. So the degrees of freedom here are the second degrees of freedom up here. So we got 37 from right here. So I'm going to do 37 equals 5.86. P is less than, got excited, less than 0.001. Oh, I want to include B. So B here is, it's like copied funny, but 27.74. So 27.74. How do I interpret that? Well, this is gender, and it's coded where 0 is female and 1 is male. So remember we talked about in the dummy coding video that this is the difference in scores. So from female to male, I get 28 point-ish increase. And that means that males are taking care of their cars better than females. And if you aren't sure, you can run just that little like fake ANOVA to get the means. And you'll see that males have higher means on this car variable than females. So one of the hardest things I think for them to interpret is categorical dummy predictors, what that B value means. And what it implies is the difference between the 0 level and the 1 level for the Y variable. So there's a 28 point difference between men and women are on the lower end here, so they're subtracting, so they have the lower score. Okay, so we're getting a 28 point increase when we're dudes. Let's calculate PR squared here. Okay. So I'm going to take this 0.69. I remember use the partial column. I don't know why it's copied so funny into Word, but what's new? And if you include the decimals, it's 0.48. So that is a lot of variance. That is a big predictor for us. Okay. Let's also include age here. So the B value for that is 0.49, which isn't totally comparable to our 27 points because they're very different scales. So let me make this a little bigger. So we got our 37 from the degrees of freedom here, and this is going to be important. It's going to change here in a second. And we've got 2.34. If we round up, P equals 0.03. And our PR squared value is this 0.36 squared. So 0.36 times 0.36 is 0.13. So I don't even need to look at beta to tell you that gender is a much better predictor. It's taken up 48% of the unaccounted for variance. And if I add that 48 and 13, I get, 61, which is bigger than this. So that's why in the last video I talked about they don't add up, they do them whatever they want because it's the unaccounted for variance. So 51% of the total variance is due to both age and gender. However, when you focus on each variable one at a time, controlling for the rest, and that's the key part right there, is controlling for the rest, you're going to get 48% of the unaccounted for variance is due to gender, and only 13 is due to age. And that's controlling for each one for the other one. However, if I wasn't using PR squared, I could use these beta values, and you can tell that the beta value for sex is 3 times age. So it's clearly a much better predictor than age. All right, all that's step 1. Now let's go on to step 2. What I want to do in step 2, now I'd recommend hitting OK here and then running the regression again. So you get it twice, but whatever floats your boat, just as long as you are clearly delineating step 1 and 2 here. Now we're just going to add extraversion in. It is additive. Do not switch them out, or you're comparing apples and oranges. Add the next set of variables. So you might do this 3 or 4 times. And then since this is our last step, and I just discovered that we can use this for our graph, let's hit Casewise Diagnostics, all cases, just so that we can make that little scatter plot graph a little easier and we don't even have to fuss with Excel. And so I'm going to hit copy, paste this over here. So in this part where we're going to talk about how to deal with all this giant mess, you can do the version that I showed you in the last video, or you can do this version. It should give you the same picture. Now in step 2 here, is the overall model significant? Boop. And yeah, it's 3 and 36 equals 21.18. P is less than 0.001, and our R squared value for this overall model is 0.64. That means the change in R squared. So I'm going to just click Insert, Advanced Symbol, and you might I always go to Font and then Symbol. Everyone should have this font. And there's a delta in here somewhere. It's very tiny delta. It's here. So it looks like AB and then delta. Oops. Close. I don't know what I just got. Oh, I got chi. Let's back up. There we go. That means the change in R squared is, oops. Let me go back up here. The original R squared was 0.51 from here. The change in R squared is going to be 0.64. Don't write it like this. I'm just showing you how I'm getting it. Minus 0.51. So that change in R squared is 0.13. Even I can math that. Okay. So when you report this, report the change in R squared. So you can report both so people can make sure you can math. But that change is important. So we've added 13% of the variance. Remember, think back to the very beginning of this video, we talked about power, and I said, let's try a medium effect size of 0.09. We actually got 0.13, so not too far off here. Well, we're way underpowered though. It told us we needed like 80 something, and we only have 40. Okay. So the bad thing about JASP here, mostly this regression stuff is pretty slick. The bad thing is that it does not tell me if that 13% is significant or not. So some of the things in SPSS and like things you can do in R, it will tell you if that is significantly different from 0. It doesn't quite have that function yet in JASP, but that's okay. What we can do is come down here and look at our predictor that we've added. And I'm gonna see if I can move this on to the next page just so it's a little easier to see. There we go. Now look at this predictor that we've added and see what happened. That's just part and partials. Here we go. So undo a couple times. There we go. I'm just going to hit enter a bunch. That'll work. There we go. I am going to ignore these bad boys because you'll notice something happened here to age. But I don't really care. So we're going to look at predictors in the step they're entered. And you'll have heard me say that in the lecture video 500 or 600 times, but only in the step that they're entered. Now this is one of those things, do what your advisor wants. That's always my number one rule. My number two rule is do what the journal wants, I guess, and then within integrity standards, and then listen to me. So here, I always ignore these variables because I controlled for them already. I already talked about how they affect things in step 1. And so to save myself some little time and energy and to not reinvent the wheel, I'm ignoring what happens to them in step 2 because I've controlled for them. I'm moving on from them. But we have to leave them in or you're not controlling for them. So here we're only going to talk about extraversion. And its B value is 0.46. So for every 1 point in extraversion, we get 0.46 CAR points, controlling for gender and age. So it's controlling for the fact that those other two variables are pretty important. They were significant. That T value, it's not 37 this time. So I'm going to scroll up. It matches the F statistic. So it's actually 36 this time, so that is a little different. And that is one way we'll know if you are following along, is that the T values need to match that model that you're testing within each step. And that's the degrees of freedom here. So I've got 3.57. P actually equals 0.001 here. And we're going to calculate PR squared. So, is the addition of that 13% significant? I would say yeah, because extraversion here is significant. So that model overall, that 64% is significant, but if I came down here and extraversion wasn't significant, it would just kind of be like, well, that's just because the last model is significant. So you can get that the overall model is significant, but that the predictors aren't doing shit for you. Okay, that is a common thing. Okay. But here it looks like this predictor is significant, so I would say the addition of it is useful. Now I'm going to come down here, I'm going to multiply 0.36 squared, which I think we did a minute ago, but we'll just do it again. So it's 0.13. So controlling for both age and gender, it's 13% of the unaccounted for variance. Okay. That is not the same thing as the 13 above. Those match just because they do at the moment. They won't always match. Oh, and then damn it, I squared the wrong thing anyway. That's why it does match, is because I squared the wrong one. We're looking at 0.512 squared. Sorry, my fault. 0.26. Okay. If you square SR, it will match, but we're going to use PR. So it's 26% of the unaccounted for variance, or 13% of the additional variance. And so what does that tell me? Well, that tells me that age and gender are important in the first step. After we control for them, extraversion is also important in the last step or the second step. Okay. And so I would write that up in order of steps. You would do step 1 model, step 1 predictors, step 2 model, step 2 predictors. You know, kind of mix and match. So last but not least, let's make that picture. So I'm going to copy this Casewise Diagnostics box only because that will save us a little bit of time in making that chart. Woohoo! And what I want, that's copied terrible, is the actual car value, which is here, and the predictive value, which I think is here. Let me go back to, so we want to ignore the first 2 numbers and use car and predictive value here. So I want to take this column here, I'm going to just stick it on in a new chart. So this is our predicted score, and then our actual car score from here. So you can do this either way. And remember, I want our predicted score on X and our Y score on Y. So that's why I put them in that order. So I just kind of flipped those 2 columns. Because then now I'm going to take my click Insert, go down to Scatter Plots, Scatter. We'll spend more time, of course, cleaning this up than we are actually making the graph. So I want to add X and Y axis labels. Okay. So our X value is 3 variables this time. So it's predicted car score, which in this particular case is age plus sex plus extraversion. And if that gets way too long, you can just say predicted score, that's fine. And then here is our actual car score. I want to add a trend line, so right click, add trend line. And remember, you can make the whole thing not blue. You want to make it black. Just kind of playing around with the coloring here. Well, I thought it was. Oh, now right now I'm getting like one little dot at a time. We'll leave the data points alone. They're being weird. We could also format colors and put the whole thing in grayscale. That would work. What's the other thing we wanted to do? Oh, change the font. Blech. So highlight the whole graph. Times New Roman. Let's make that 12. I can also click on border. Let's click format. Go away. Give me no border here. Oops, not automatic. No outline. So when I cut and paste this, it'll paste into Word nicely. Depending on the day. Depending on how Word and Excel are feeling that day. Right. There we go. And that will show us, look how close we are. So remember in the last video, we weren't really doing very well at predicting the top end of the data. I said, well, we're not getting the people who are making A's very well. We're doing a kind of a crappy job at that. And that's because the R squared value is lower. As R squared gets higher, what you'll see is the dots are going to be much closer to the line because you're doing a good job of predicting people's scores. And so since this is fake made up data, we're doing a very good job of predicting people's scores on purpose. So that all together, we started with just checking your data for missing data. We did power. Checking your data for data screening, and then we did power. We talked about how to do each step. Remember, keep the steps separate from each other. Talked a little bit about writing them up, and then ended with creating a picture of our predicted scores.